Anyway, so the sheet you see here is pretty much what the exam looks like. Now, because it covers a whole semester, I am going to give you a little bit of a break. One thing I will do is I'll have a certain number of blockouts. I haven't decided exactly how many yet, but if there are 150 questions, then it's possible I would have maybe 10 blockouts. Now, a blockout would mean that you just put a block in the answer sheet for number 3 and said, well, that question doesn't exist for me, and that won't count against you. Get that? And so that'll be kind of like a curve. If you curve the exam, if I let you have 10 questions you don't have to answer, that should help your grade. The other thing I'm going to do is I'm going to give these to you today. If I get these ahead of time, if I get these before the exam on Tuesday, okay, you probably should try to give it to me tomorrow, but because if you don't remember on Monday, then I'll make a list and say you can't use these. But what I'll do is I have some cards. I'm going to reuse them, and you can write on one side. And whatever you want to write on one side, you can take that to the exam. You're not going to take it. You're going to give it to me, and I'm going to staple it onto your exam. Get that? So the teacher's going to be told they can't use this unless it's stapled to their exam. So anyway, since you already got up once, if you'll give everybody one of those. Now, some of you are really strong on this chapter, and you might want to write a little bit. You might want to write a little bit about this chapter. And then some of you might want to write something about the mole or how to do a mole problem. Some of you might want to do a limiting reacting problem. You might want to do one of those on the card. I think some of you, your weakest points for some of you were writing formulas and naming compounds. I could see maybe putting one example of each one. How do you name this? How do you name this kind? You see that? That should give you a good advantage. You get that? Some of you feel pretty good about this. If I give you blockouts and I give you this card, I think you should be able to do the rest. Okay? And I think you should be able to get a decent grade. All right. Everybody got that? Okay. Can everybody almost see what they have to do then? Everybody see what they're doing? All right. Well, let me go ahead, and the last thing that I didn't get to do on chapter 11 is, as we look at the periodic table, let's take a look at one. Try to find one. Madison, can you give me, on that table there, find a little periodic table. I usually have one right here. Thank you. All right. All right, so let's take a look at the periodic table, and let's see how much you know by just looking at it, okay? From the first semester and this semester, what do you call these things here that go this way? What do you call the horizontal parts of the periodic table? Periods. What do you call these? They have a special name for the columns. They're called groups or families. So if somebody says, what family or group do you belong to? What's the special name for this one? Remember the alkali metals? Remember that? Okay, what is this one called? Alkaline earth metals. Okay. As a matter of fact, see a stair step? See a stair step? Except for hydrogen, everybody on this side of the stair step is a metal, isn't it? Most of the elements on the periodic table are metals. That means most of the elements want to lose electrons. And then who wants to gain electrons? This little tiny group up here, right? Those are the nonmetals and hydrogen. And then what about the noble gases? What do they want to do? Do they want to gain or lose? What do you think? Neither. Their electron configuration is so stable, they don't want to form compounds. They don't want to gain or lose or share. Everybody got that part? These are noble gases. What do you call that group right there? They use that term in your book, and even in this chapter. Anybody know what these are called? These are the halogens. Remember that? Now the rest of them, and then two more. What do you call this group of elements right here, this box right here? Not what block is it, but what did you call it like in the first semester? Excellent. Transition metals. Everybody see that? And then these are called the lanthanides because this one comes right after lanthanum, and they all act like lanthanum. And these are the actinides because they come right after actinium, and they act like actinium. Now, in this chapter, here's what you learned. So I'm going to get a pen here. what do you call, in this chapter, what did you call these two columns in this chapter? All right, now what does that mean? The S block means that you're either putting one electron in the S orbital or what? Or two, remember that? All right, what do you call this box right here? And there are 6 columns here. What's that called? P block. That means you're either putting 1, 2, 3, 4, 5, or 6 electrons in the p orbitals. Okay, what do you call this part right? Whoops. What do you call that part right there? All right, D block. That means you're either putting 1, 2, 3, 4, 5, and it can hold up 10. It can hold up to 10 electrons. That's why there are 10 here. And the one we didn't spend too much time on are down here. In this chapter, they would call that not S, not P, not D, but what's this one? F block. And that means they're trying to fill in F orbitals. Now, again, I don't spend a whole lot of time in first year chemistry with the F block. All right, what do you think? Now, the other thing I'm going to show you, and this is the last thing in the chapter, that what if I ask you, I know I told you this before, but remember the Roman numerals? What do the Roman numerals stand for? Why would I want to look? I know what the period stands for. It says we have all of our electrons in only the first energy level. I have at least 1 electron in the first and the second energy level. I have at least 1 electron in the third energy level, 4th energy level. See that? That's what the periods mean. But what do the Roman numerals stand for? Like 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. What does that stand for? Layla, what do you think? And I know it's early in the morning, and we mentioned this several times, but see if you can come up with it. What do you think the Roman numeral stands for? Like, why are all these elements in group 1A? What do they have in common? They have what? They have 1 what? What are the electrons called that are involved in chemical reactions? Starts with a V. Valence electrons. Everybody here has a valence. You know why? You know why they put them together? Because they act the same way in chemistry. They violently react with water. They all want to form the same type of compound with chlorine. 1 of me and 1 of you. And that's why they put them in the same group, because they act the same way, because they have the same number of valence electrons. These all have 2 valence electrons. These have 3 and 4 and 5 and 6 and 7 and 8. Got that? And what do you call an element that has 8 valence electrons, except for helium? Noble gas. And everybody else wants to try to put their electrons like the noble gas does. Why do you want to be -1? Because if we gained an extra electron, our electrons would be like the noble gas closest to us. Why do you want to lose 1? Because if we did, the remaining electrons would be like the noble gas closest to us. That's chemistry. That's like all of chemistry in 2 sentences. The last thing I want to show you is, what do you think would happen if I went down a group? What if I told you that hydrogen was this size here? How big would lithium be? Would it be bigger or smaller? It's like the last 2 pages of chapter 11. Anybody know? How about a guess? If this is hydrogen, what would the next element be? Lithium. Would it be bigger, smaller, same size? What do you think? It has the same number of valence electrons, but where's my valence electron in the first energy level? Where's your valence electron in the second energy level? Does this make sense to you if I said you only have 1 energy level, you have 2 energy levels, you have electrons in 3, 4, 5? Does it make sense to you that the atoms get what as you go down? Does it make sense to you? In every case, I can go down this column, down this family. Aluminum is bigger than boron. Silicon is bigger than carbon. Bismuth is bigger than antimony. Because they have another energy level that makes them bigger. Is that pretty easy? That's pretty easy. Now, there are companies that actually work on that. They know the size of the atoms, and they try to make things. I saw a special on how they were making bulletproof glass or near unbreakable glass. And they were trying to squeeze other kind of ions into space between other atoms, and that's how they were able to do it. And so it all had to do with atomic size. Now, this is kind of intuitive, that as you go down, the atoms get bigger, right? But here's what's not intuitive. Does anybody know what happens as you go left to right? So they certainly get bigger if you go down because you're adding new energy levels. But what happens as you go left to right? Anybody? They do. They get smaller. And here's the theory. The theory is that all these electrons are in the second energy level. They're about the same distance away from the nucleus. And what are you doing as you go left to right? You're adding 3 protons, then 4, then you have 5 protons, 6, 7, 8, 9. And the idea is that if you have more protons pulling on electrons, they tend to pull them all in a little tighter. And so these it actually gets smaller. The atoms get smaller as you go left to right. So I make this a little smaller, like that. All right, that's the last thing I want to do on that chapter. And one more time, because there are a lot of questions on that chapter, we haven't had a test on it. Please make sure you said, I'm absolutely ready for that chapter. I can get ready for that. All right, now we're going to switch gears, and we're going to go to back to stoichiometry. So if you have your test file folder with you, let's go to, I'm using Zach's test here. There you go. Use Zach's test. Does everybody have this? All right, so if you have a calculator, all right, I don't want you to do anything else right now. Don't do any math or anything now. Tell yourself, if I saw questions like this again, I could do well with them or not. Okay, pick a question on this page, 1 through 7, and said, wow, if I saw that one, I don't really want to use a block out if I don't have to. But if I saw one of those, also you're going to be limited in how many block outs in each column. So you can't just say I'm going to block out, 8 of these kind of problems. You won't be able to do that. Can you look right here and just say, let's pick about 2 or 3 of these and do them and say, hey, I'm feeling better. I'm feeling better about these kind of problems. How about number 2? Can I do number 2? Can I give you a hint? If you'll help me more, I know you can sit there and say, hey, just spoon feed me. Tell me what I need to know. I've been doing that all year. But what you need to do is say, what is it that I still have trouble with? How about number 2? Would you bet $100 that you would get that question right? Ooh, I like that. I like when you shook your head like that. I like that. We're not going to do any betting. But if you can't bet $100, you said, well, you're right. I really don't know what I'm doing there. Let's do number 2. We see that this one's balanced, right? Everybody see that? And it has a 1 here. You don't see the 1. And a 6 and a 4. And it says, what if I had 8 moles of hydrogen? Now, let's go over here. So I draw a little box down here. And it says, what would happen? So here we go. Ready? This is what we did a lot on the last test. These are when I look at these coefficients, when I go sideways in the mole world, I pay attention to the coefficients, don't I? And that's called a mole ratio. When I say 6 and I go this way, what would you say? 6, 1, gotta get smaller. You guys need your calculators out. Everybody get your calculators, okay? Tell me what I would put here if I had 8 here instead of 6. Then what ratio? I got to maintain the same ratio, right? If this is 6, this has to be 1. But what if it's 8? What is it going to be? You say, gotta get smaller. So you're going to multiply this times what? It's going to be 6 over 1 or 1 over 6. Okay, let's do that. Put your calculator. What do you get? What's 8 times 1/6? Tell me, Dan, do you have it? 8 times 1/6. 1.3. Okay. Okay, now, let's go over here. Now, what about this one? Gotta get big. Wait, gotta get smaller. Gotta get smaller. What are we going to multiply now by? 6 over 4 or 4 over 6? Which one's going to make you smaller? What do you think, Layla? Okay, go ahead. What's 8 times 4/6? 5 point what? Okay, now we're ready to answer the question, aren't we? If 8 moles of hydrogen, would it react with 4 moles of phosphorus? No, you told me it was 1.3. That's out. Would it produce 16 moles of pH3? No, you told me it was 5.3, right? Would it not react? No, it reacts. Would it produce 5.3 moles of that? You say ding, 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 ding. Okay, everybody see that? Does that sound right? Now, some of you are really strong on this chapter, okay? Tell yourself, okay, what are these? Let's do another one. Let's do another one. Are you okay on that one? Let's try another one. Let's go right here, number 4. Now, if you have your calculator out and you're pushing buttons, you're probably going to get more confident. If you're just sitting there, you're not going to get more confident. You're going to say, oh, I don't know if I'm going to do well. Don't do that. Make yourself do well. All right, a 1.9 mole sample of this was decomposed. Now, since they already gave it to me in moles, if they had given it to me in grams, I would have switched it into moles right away, wouldn't I? What's the shortcut? If they had given it to me in grams, what's the shortcut to go down in the mole world? Divide by what? The molar mass. Okay, but you know what? They already gave me moles, so I'm going to put it right here. 1.9. Now, this is just like the problem we did. And it says like this, and let's find out how many moles of this. So watch, 2, 3, 2, 3. Got to get bigger, so you're going to multiply by 3/2. All right, Madison, what do you got on that one? Oh, no calculator? Okay. Isabel, do you have a? Say it again. All right, let's take a look. And wow, that's always good. When it's multiple choice and you see the answer, that makes you feel good, doesn't it? All right, what do you think? All right, let's see. What else? Okay. Okay, how about this question 6? True or false? A mole ratio, and that's what we were doing when I said multiply by 3 over 2. A mole ratio is used to convert moles of one substance to moles of another. Is that true or false? Isn't that what we've been doing? We changed moles of something into what? Into moles of something else? Yes? So we did use that. All right, let's flip it over. Let's go to the next page. Now, we'll get to the hard ones in just a minute. All right, let's take a look at this page here and say, all right, some of these are kind of the same. Let's see if I can find one. All right, let's do number 14. Can everybody go to number 14? Everybody go to number 14. All right, everybody go to number 14. It says it's unbalanced, so you can't do any stoichiometry without a balanced equation, right? All right, can everybody help me balance this one? It's a combustion reaction. We have to be careful about combustion reaction, don't we? When I look over here, I know you want to put a 6 here, and I can draw a 6, but I'm probably going to erase it because look at what's going to happen here. This 14 hydrogen, you want to put a 7 here. But we taught you that before. I taught you that on a combustion reaction, you don't want an odd number in front of the water. Is that right? So what do you do? How do you fix that? Do you remember that trick? Kyle, do you remember that trick? I'm not going to put an odd number in front of the water for combustion, so what do you do with it? Double it. All right, everybody see that? So let's put a 14 here. So everybody put a 14 there. So now, if that's 14, that's 28 hydrogens. How do I get 28 hydrogens here? I put a 2 there. Now how many carbons do I have? 12. Okay, we're getting close now. Let's find out how many oxygens on the right. 12 times 2, 24. 14 times 1, 38 oxygens. Okay, now how do I get 38 oxygens here? All right, Aurora, what do you think? How do I get 38 oxygens there? Real loud, I can't hear you. 19, excellent. Well, now we can do our problem. We got a balanced equation. And first of all, if they give me excess of whatever, then I don't have to worry about 2 rows of boxes, do I? It's only when they give me either grams of both reactants or moles of both reactants. That's the only time I do 2 rows of boxes. All right, so here we go. In your calculator, let's go ahead and put 11.2 here, grams. All right, ready, shortcut, go. Go down in the mole world. 11.2 divided by the molar mass. That's pretty nice. Gave you the molar mass, didn't I? Let's try it. Put 11.2 in a calculator, divide it by 86. See what you get. You don't have a calculator with you?
Oh, I already did it.
Okay. Oh, you already did it? Oh, good. Okay. Sarah, what do you have here? What do you have for moles here?
I got
I'm sorry, I can't hear.
I got 0.130.
0.1. I can't hear. What? 1.3? 0?
2, 3.
Okay. That's 3 sig figs? Okay. All right. So now we want to go over here, don't we? So we look over here and say 2, 12. Got to get bigger. So I'm going to multiply by 12 over 2, which is 6, by the way. So you figure that out. And that looks like it's going to be an 8, carrier 1, 0.78. Is that what you got? Uh-oh, we got a problem here. Oh, I'm sorry. That's, I'm going to reread the problem here. What mass of carbon dioxide? We found out moles, didn't we? So how do we go up? How do you go up out of the mole world? Multiply, and what's the molar mass? Uh-oh. What's the molar mass of CO2? And I was nice to give you this one, but what's the molar mass of CO2? How fast can you do that? 40 what? 44? Very good. So, okay, take 0.78 times 44, and do you already have it? Did you already do it? Okay, take 0.78 times 44. What do you have? 34.3. And there we go, right there. What do you think? Can you be pretty strong on these or not? All right, now, the hard ones. They start, well, let's do this one. Let's go ahead and do, let's do this one, and then, it says question 16. We'll do these, and then we'll be done with that. Unfortunately, that blue box is not going to be in the room you take the exam in. In this periodic table won't be there. You'll get your own periodic table, but you'll have to remember that number, 22.4, okay? 1 mole of any gas is 22.4 liters, so we'll do this one after we do this one, all right? How many moles of oxygen are produced? They want to know moles of oxygen are produced by 27.2 grams. 27.2 grams, so you did that. And, all right, really? Let's do shortcut. Divide by the molar mass. So let's take 27.2 divided by 34. May, do you have that? We got 27.2, and we're dividing it by the molar mass. What do you have? 0.08. Is that everybody else got? Now that's only 1 sig fig, so it was 0.0800 or something like that? Yeah. Okay. All right, now when we go sideways in the mole world, and good, they balance it for me. 2, 1. Got to get smaller. Multiplied by half. You said 0.08, so it's going to be 0.04. Oh, wait a minute. Did you say 0.8 or 0.08? 0.8? My fault. 0.8. Okay, sorry. This would be 0.4 then. Okay. There you go. Now, we're almost done. Let's look at this question. In question 16, how many liters of oxygen What's the shortcut for that? You got 0.4 moles of O2. What's the shortcut? I'll do the long cut. Does anybody know the shortcut though? Like 1 mole of any gas is equal to 22.4 liters. What's the shortcut? Moles times what? To get liters, moles times what? What do you end up doing? Moles times what? 22.4. Go ahead and put that in the calculator. What do you got? Who haven't I called on yet? Delaney, what do you got for 0.4 times 22.4?
8.96.
And one more time.
8.96.
Okay. What do you think? See, I think I know more than I thought. All right, are you ready to do the harder ones? If you'll stay with me and you'll work hard today, we can get through this. We do the mole concept, and we can be ready. I think you can be ready. Now, I don't on the exam. I don't necessarily tell you that they're limiting reactant, but how do you know? Either I give you the grams of both or the moles of both reactants, right? And that's when a little bell goes off in my head, and that's when I start doing 2 rows of boxes. So let's do number 21. All right, would everybody try it on your own? Try it on your own and see what you get. I see that Zach started here, and let me see if he did it right. First of all, I have a balanced equation. That's good. And it says here I have 11.9 grams of Cl2. So he put that in. I like that. Now, if he divided by the molar mass, if he divided by 71, if that's correct, then he's in the right, doing it right. Now, what do you do with the NaOH? 10.9 grams of NaOH. But when we convert that to moles, we don't put it in the same row. We put it in another row. You see that? This is the story told by the peanut butter. This is the story told by the bread. The peanut butter says, we're going to make this many sandwiches. The bread says, I don't think so. And so we have 2 stories going on. We have to find the limiting reactant. All right. Does anybody I know Zach didn't fill these in, so I don't know what that is. But what's 10.9 divided by 40? What's 10 point? You could use your phone if you wanted to. You have a phone? You can use your phone. Somebody help me out. Sierra, what is 10.9 divided by 40? Sorry. 0.77?
0.27.
Wow. It sounds like you're saying 0.27? 0.27?
Yeah.
Okay. All right. One day we won't be wearing these. Okay. So now here we go. This is the hardest part of the chapter. How do you find out who the limiting reactant is? Here's what we're going to do. This asterisk says, I know you brought that much peanut butter. This asterisk says, I know you brought that much bread. We need to fill in one more box. Get that? So let's go from here to here. 2, 4. 2, 4. Gotta get bigger. This looks like it's going to be 0, 7. Is that it? 0.67? Is that what you got? Am I doing that in my head right? So if I go from here to here, multiply by 4 over 2, which is the same as 2, 0, 7, yeah, that's it. Now, we're ready to tell a story. I brought this much peanut butter. I need this much bread to use up all the peanut butter. Did you bring me that much bread? No. Yes?
Why'd you put the 0.335 in the first one?
Well, I assume that Zach did that right. Maybe I'm wrong. Okay, can you tell me what is 11.9 divided by 71?
I think it'd be 0.167.
Oh, no. That's why you missed it. Okay. What is it? 0.1?
0.167.
Okay. I made a mistake assuming that he did it wrong. That's my mistake. Okay? All right, so here we go. Now we got to change this number, don't we? All right, so what's this number times 2? 0.167 would be 4, 3. Is it 0.23? 0.234?
0.334.
What?
0.334.
334? Okay. Okay, now, we're ready to tell a story. I brought this much peanut butter, and I need this much bread to use up all the peanut butter. Did you bring that much bread? And the answer is No. So you are the limiting reactant. This chemical right here and this amount here is going to tell the story. So this whole story should be right down there. See that? Okay, so what do you want to know? How many moles of NaCl are produced? All I need to do is go right there, and I'll be done. So let's go 4, 3, 4, 3. Got to get smaller. So I'm going to multiply by 3/4. And what'd you get? What's 0.27 times 3/4?
0.204.
Is that right?
0.204.
I wish I could hear you word better.
0.204.
Is that what everybody's getting? Okay, is that answer on there? Please be on there. Oh, yeah. Okay, what do you think? I actually was very impressed when you guys took that. I thought that is not one of the easiest chapters, but there was something mathematical that you clicked on, and you seemed to do better there. So, all right, what else? How about, let's go over here. Let's do some vocabulary words, okay? I think some of the easiest ones are vocabulary questions. For all gases at STP, standard temperature and pressure, 22.4 liters is their what? What do you think? And again, that blue box won't be there, but what do you call that? For any gas, 22.4 liters is what? Molar volume. It's the volume of 1 mole of gas, molar volume. Okay, what about number 2? Blank is the mathematics of chemical reactions, calculations involving mass of products, mass of reactants. What's that word? Stoichiometry. 31, the chemical that can be determined. It determines how much product actually will be made. Is it the peanut butter or is it the bread? So what are you going to call it? What's the one that actually determines what's going to happen? The limiting reactant, okay? What do you call the calculated amount of product? When you do all your calculations, but you don't get any lab equipment out, what do you call the calculated amount of material? Theoretical yield, yes. What do you call, if you actually do the experiment, how much you got? Actual yield. And what do you call it when you take the actual yield and divide it by the theoretical yield times 100? What's that called? Percent yield, right? And percent yield is percent of correctness. Like, hey, I could have gotten 8.5 grams, and when I did the experiment, I got 8.1 grams. So I could figure out my percent of correctness, can I? All right, let's do another one. To convert a mass of one material to the moles of that same material, mass to moles, what would you do? If you have the mass of something, you want to convert it to moles, what do you do? Divide by the molar mass. Excellent. In order to calculate the percent yield for a chemical reaction, someone actually has to do the experiment. Yes, and you guys did that right. That's the last thing I haven't graded for you. I had to grade your lab right up. You did. Next, when converting moles of X to moles of Y, that's like this. That's like going sideways in the mole world, right? The conversion factor is called what's that called? Mole ratio. That's right. Okay. Okay. I guess we're okay on that. Again, I know you did well in this chapter, but I don't want to gloss over it and say, we don't have to study it. All right. You okay with that? Okay. Let's go back and let's find the chapter called mole, the mole concept. Tomorrow, we'll do balancing equations, classifying, and writing formulas. We'll do that tomorrow. Okay, mole, here it is.
You said that the first page is going to be like vocab for the...
But only for chapter 11.
Right.
There could be vocab on other questions.
Like, I know we've gone over it in class and stuff, but I don't know. Like, is there a place where it's like all written down?
Well, do you have that practice test I gave you?
Yeah.
All right, let me double check that practice test, okay? this one right here, this page right here, do you wanna go over those? Do you wanna go over the answers on those?
Well, we have
Right.
the answers, so,
Oh, you do? Okay.
actually, like, is that the vocab that's gonna be on
Well,
the test?
again, I'm not here to say, here's the exact, 18 vocabulary words, okay? But if you know 18, there's about 18 here probably, so, yeah, I would say that's a lot of them right there. Yes?
Can I have a copy of that worksheet?
Okay. Okay, I'm gonna find it, because I gave these out several days ago. I'll try to find it. Here's also a list of vocabulary words. Let's see. Okay, here you go. I'll tell you what, I might have to, let me think about this. I had these out for several days. Oh, there they are. Good. Dinesh, you can get that right there. Anybody else need one of these? Anybody else not have one? Okay. Let's go to, we only have about 6 or 7 more minutes here. Let's go to the test called, ooh, look at that. Look at that. Ooh, hey Zach, see that? That was a good test for him. What? All right. Let's take a look at this page here. And this is where it all got started, the mole concept, and then we did things called percent composition and empirical formula. And this is kind of a hard chapter because it was the first time we did a little stoichiometry. Okay, look at number 1. This is some of the easier questions. What is an empirical formula? What do you always know about an empirical formula? Like I said, which of those is not empirical? Empirical, the definition, I'll give you the definition, it's the lowest whole number ratio of the elements in a compound. For example, last year in you did glucose, C6H12O6. Is that an empirical formula? You say it can't be. Empirical formulas are always reduced to the lowest ratio. So I can divide all these by 6, can I? CH2O. This is a real chemical, but this is the chemical's empirical formula, isn't it? Yes? So which one of these is not empirical? Right, it can't be. It's not reduced. See that? Now, I threw this in there to throw you off a little bit, but this one, we did a lab. One of the labs we did it's called a hydrated crystal. And when you heated that blue stuff, steam came out of the test tube. Remember that? And so, but that's a special case. But that's also reduced. It's already reduced. So it is empirical. All right, here's another one. Next one. What is the percent by mass of aluminum in aluminum sulfate? And when we taught this, we said whenever you do percent, you always divide by the total. So let's find out the total mass. What is the total mass of that? And that's a skill you have to have. Okay, so you got to take your time. Look on the periodic table. Use your calculator. How much would 2 aluminums weigh? How much would 2 aluminums weigh? 54? Okay, so 54 is the 2 aluminums. And then how many sulfurs do you have? Or do you want to do it this way? Would you feel better doing the sulfate and then multiplying by 3? Or would you rather do 3 sulfurs, 12 oxygens? Which one works better for you? Do you want to do the whole sulfate and then multiply it times 3? Or do you want to do 3 sulfurs, 12 oxygens? Why don't you decide which one works better for you, okay? Let's do it now. Tell me what this part would weigh. How much would it weigh? And I see what Zach put down. It looks like he did 3 times 32. He got 96. And then 12 times 14. I mean 12 times 16. And is that right? Okay, so the total mass is 342.3 or somewhere around 343. But how much of that mass was aluminum? Out of the 342, how much was aluminum? And we figured out 54 of the 342. And I don't know if he finished his problem or not. Daniel, what do you have for this one? What's 54 divided by... Are these numbers correct, first of all? I'm using someone else's test. What's 54 divided by 342?
Point 15.8.
15.8. And remember that 0.158 is the same as what? 15.8%. Is that correct? So that's why you got that right. What do you think about that? All right, now let's do a harder one. What is the empirical formula of a compound that is blah, blah, blah percent nitrogen and blah, blah, blah percent oxygen? This is something you probably forgot, but if you want me to find a formula of anything, you cannot be in the gram world. What world is that formula in? It's in the world of number of particles. Now, what other four-letter word do you know that means I'm in the world of number of particles? Moles. So what we do is you play a little trick here. See that? I change this to grams. I say, hey, you gave me 100 grams, I'll bet, and 25.9% of 100 grams was that. So 25.9 grams were nitrogen. See how you put a little G there? Okay, now, I'm not done because I'm not in the mole world yet, am I? So what do? Divide by the molar mass of nitrogen. That was 14. Now, look how he was using factor label at the time because I hadn't shown the shortcut. Everybody see that? I hadn't done the shortcut then. But you did divided by the molar mass, and he got his funny-looking number called 1.85. Then he took this and divided by the molar mass of oxygen, 16, and he got a funny number looking like 4.63. Now, this is where, long time ago when I learned this is where I got stuck. I had these funny looking numbers looking at me and I didn't know what to do. What do I do next? What's that little math trick that'll make these look a little bit more like whole numbers? Roar, what do you think? Do you remember that little math trick? I had 1.85 looking at me and 4.63. If I want the empirical formula, it's got to be the lowest whole number ratio. And they don't look like whole numbers, do they? Do you remember that math trick? You divide by don't say molar mass. Divide by, you guys are certified. Just kidding. You are certified. But when you had to be certified, you had to divide by the smaller of the two. Which one's smaller? 1.85, right? Now what's 1.85 divided by 1.85? 1. And what's 4.63 divided by 1.85? Oh, it's getting close. It's getting close. Now, how can I make both of these? Whatever I do to that number, I have to do to that number. Got that? I need a whole number. What am I going to do with 2.5 to make it a whole number? Multiply by 2, that's 5. Multiply this times 2, and that is 2. I think I have the answer now. Nitrogen, 2. Oxygen, 5. That's about the hardest of that kind of problem I could give you. Get that? But if you don't review that, I can see you just completely going a blank. But if you review it and you try it a little bit, yes, Sierra.
So if we do that and we divide and it equals maybe 2 points.
Okay, good question. Now, if it came out to be like 1.99, that's 2. What about 2.02? That's 2. But 2.3 would not be 2. And 2.4 would not be 2. Get that? But you're right. If it's really close to a number, it's 2. Yeah, what's your question?
So if it's like 2.4, how do we write that?
Okay. Normally, it won't come out to be 1 and 2.4. It might come out 1 and 2.49. It might do that. And that's like 2.5. But I'll never give you a problem. That's a great question. I'll never give you one where it's 1 and 1.85. That's never going to happen. And so that little trick about dividing by the smaller of the two numbers, that's a neat little math trick to make ugly looking numbers a little bit nicer. All right. Let's see. Okay. All right. Let's see. How fast can you do this one? Is this can you do some pretty fast? What is the percent of oxygen by mass in KNO3? And I'm nice here. Look how nice it was. Gave you the molar mass. The whole thing weighs 101. Oops. whole thing weighs 101. Oh, I gotta stop. Okay, how much does the oxygen weigh? 3 times 16. So it should be like that, right? Hey, you know what? Thank you very much. At this point, you're making me feel good